Hello everyone, I'm Daishen Li, a first-year PhD student from UC. Today, I'm very glad to present UniHeap, managing persistent objects across managed runtimes for non-volatile memory. This work is in collaboration with my advisor, Professor Jian Huang, and other collaborators in UC. Nowadays, non-volatile memory has become a promising technology. It offers near DRAM speed, scalable memory capacity, byte-addressable interface, and data durability. However, the biggest challenge is that programmability of non-volatile memory is still a problem which hinders the widespread adoption of non-volatile memory. Why is the case? It is because in modern memory hierarchy, many levels of volatile cache exist between non-volatile memory and the processor. The order of an object update to be persist depends on when it is evicted from the volatile cache. In order to ensure the persistent order, we need explicit instructions, for example, cell BB and sfns in x86 processor. We also need to mark all the persistent updates in the code. If we miss a single one, we will be correcting this problem because we do not persist the target update. If we have redundant instructions, there will be performance bugs because we suffer from redundant flush. So you can see programmability of non-volatile memory is still the biggest challenge. To address the programmability issue, we can leverage managed runtime to manage non-volatile memory. There are mainly for two reasons. First, managed runtime can transparently manage hardware complexity and data objects, which make it practical to provide easy-to-use API. Another reason is that managed runtime is broadly used in many popular programming languages such as Java, Python, and JavaScript, which means this solution could become pervasive. Our previous work, AutoPersist, only required developers to mark the durable root objects with a simple annotation as shown in this figure. Then the managed runtime will automatically and transparently persist all the reachable objects from the durable roots. Comparing to previous work, AutoPersist achieves 16 times less persistency markings in the program, which significantly improve the programmability. However, AutoPersist can only support Java language. How can we extend this to multiple runtime, for example, Java, JavaScript, and Python? Because non-volatile memory is a storage device and is a system-wide shared entity, of course, we need data sharing. If we think about how traditionally storage device do data sharing, which is file system, so file system enable data sharing across different programs with a file abstraction. So our runtime managed non-volatile memory framework is also naturally desired to enable the data sharing with a persistent object abstraction. In this case, we consider our managed runtime as a new file system for non-volatile memory. There are various real-world scenarios that also need data sharing across multiple runtimes. For example, web services share persistent objects between server and different clients. Shared libraries enable multiple programs concurrently access shared persistent objects. In data analytics, programs concurrently analyze and manage shared persistent objects. So in these scenarios, we see that object sharing among many runtime are needed. So to enable efficient object sharing for non-volatile memory, we present UniHeap, a new NVMW framework for managing persistent objects. UniHeap consists of a unified persistent layer that has a unified object model for various managed languages and a shared NVMe heap that enable cross-language object sharing. UniHeap also optimizes the data layout to reduce persistency overhead. Achieving this is not easy. There are three challenges we need to overcome. Firstly, we need a unified object model and type system for object sharing among different runtimes. Secondly, we need to ensure both persistency and crash safety with low overhead. Thirdly, because many runtime naturally need to do garbage collection for the user, we need to build an efficient and correct coordinate GC. Now let's look at them one by one. We achieve unified object model and type system by providing two built-in types, numerical type and reference type. As shown in this table, the numerical type covers the commonly used types. The reference type's object field stored a pointer to runtime-specific persistent objects. So based on this design, different managed runtime can then map their type to the type system of UniHeap. We achieve the efficient persistency implementation by reduce the persistency overhead. The traditional way of ensuring persistency, undo and redo logs, which need to write both the log and the data to persistent memory, bring duplicate write overhead. To reduce the object persistent overhead, UniHeap leverage both atomic update and auto-place update. We only need to append the update data to the NVM once, so it will reduce the persistency overhead. We show how we put the optimization into the UniHeap system. So UniHeap manages the persistent objects in a log structured manner. We store persistent objects in a shared NVM heap. We decouple the data and metadata of objects based on the observation that metadata is not frequently updated in a transaction. We enable auto-place update in data log region, ensure data crash safety and support concurrent access to the object. We also design GC to reduce the server overhead of the log region. We optimize the late data lookup for the read operation with an object index table stored in the DRAM. With all the above design, we can achieve an efficient and crash-safe persistent object management. For efficient and correct GC, because each runtime have their own GC, we also need to coordinate GC across many runtimes. UniHeap tracks object reference and reachability from runtimes with vroutes to achieve this property. For the detailed GC algorithm, please reference to the long video. UniHeap framework is implemented as a shared library, including the unified interface and the log structure object sharing. The shared library enables fast access to the shared NVMe heap through direct memory access. In our evaluation, we find that shared overhead is low comparing to Swift and shared memory solutions. This is because Swift has to conduct serialization and deserialization operations, and shared memory do not have data persistent optimizations such as our log structure persistent object management. For further details, please reference to our long video. Thanks, and I'm happy to take your questions.